Let's now kind of talk about what we've essentially been building towards for the last 12 lectures, but we did not know it, which is Gauss's law. So in class, we had a lot of motivating problems. So you should definitely look at those sheets if you have not yet. We have one example of our good old streamlines with water, where I said, what would you say is the case when you have a hot water tank where you know that 3 streamlines go into the pipe, and they go throughout your house. They're supposed to go directly to your shower, but then when you turn on the shower, only 2 streamlines come out. Well, it seems like there was some sort of sink, and I don't mean actually sink in the bathroom, haha. But and that 3 streamlines go in, 2 streamlines. I just thought of that. 3 streamlines go in, but then only 2 came out of this kind of mystery box. So something had to take away one of those streamlines. So we'd say there's a leak. There's somewhere else that the streamline went. And we also saw, when looking at charges, if I had a positive charge, that the field lines go out of a surface I could draw around the charge. In that case, the flux was positive. Again, with the convention that the area vector points out of the volume. And for a negative charge, same thing, but the field lines are all going in. There, the flux was negative. And then if I had some volume that was closed still, so it closed a volume, but then I had a charge outside, all the flux lines or the field lines that go in also came out. In that case, there was 0 flux, or 0 net flux rather, into this volume. There was some positive flux on this surface, but then there was a negative flux on this surface. I guess the flux ended up being 0, where there happens to be no charge inside this thing. And we had another example where I said we can think of flux as counting field lines. So I had kind of a biased dipole here, with a 2Q and a negative Q over here. And I asked us to look at various surfaces where I had, and I said just count the field lines. So for the red one here, we could count that 16 field lines went out, 0 came in, a net of plus 16, again, without being positive by the convention. It happens that that box also has a net charge inside of it of 2e. And take the blue box. 8 field lines go into it. So the 0 went out, 8 went in, a net of negative 8. And it happens to have negative e inside of it. So we got plus 16 was 2e, and then negative 8 was negative e. Seems like there's some relationships forming. Then we got this gold one. 3 went in, 3 went out. Net 0. And there was no charge inside that box. Same for this green one. 2 went in, 2 went out. No net charge inside of this thing. And this purple one essentially looks like the blue box, but then it kind of goes all the way over here, loops over, and then goes back. So all these 8 still go in. But then we got this one where it goes in, but then comes out again. So 1 went out, 9 went in, still a net of negative 8. And the charge inside that box is still negative e. And then the entire box itself. 11 went out, 3 went in, net of plus 8. And the net charge in this case was plus e, which happens to be the net total charge, because there's plus 2 minus 1. So all these are motivating that for a closed surface, and again by a closed surface meaning some surface that encloses a volume. It could be a solid surface, or a surface of a solid, like the outside of a sphere. It could be, like in the previous video, kind of the volume of a kind of, if you imagine 2 spheres, right, where one's a cavity, but then the volume that's kind of this part, that's a closed surface. That the total flux through that surface, in this little circle here, just a calculus fancy way of saying that the integral is over a closed surface. So a circle just means that it's over some sort of surface that encloses a volume. It's not just a sheet. A sheet doesn't enclose a volume. A circle doesn't enclose a volume. the surface of a sphere, that does enclose a volume. The sides of a box, that does enclose a volume. So the integral of the flux over a closed surface seems to be proportional to the charge inside the surface. That's why we need to be closed. And that's, again, this case here. All these closed surfaces seems there's a relationship between the net flux and the net charge. This could motivate kind of a relationship where it seems like we should be able to say that the flux is proportional to the charge enclosed. And again, to be proportional just means that you're related by a constant, right? So essentially saying that this is equal to some constant times Q enclosed. We could, as a way of motivating the proof of this, if we want to call it a proof, we could then take as experimental evidence Coulomb's law and say that, okay, we've measured and we know the answer for Coulomb's law. And we did this in the last video, where if you have a positive charge and I have a spherical surface surrounding it, then the flux, or the field lines that determine the flux, are all going out of the surface, and they're all parallel to the little dA elements. They're all parallel to the surface at that point. And since they're all the same distance away from the charge, some distance, capital R say, then we know that the magnitude of the electric field is the same at each point on the surface. So again, if we take Coulomb's law as experimental evidence, meaning that we know what the electric field is, then the total flux is going to be Q over 4 pi epsilon naught R squared. And that's multiplied by the area of the sphere, 4 pi R squared, which seems to then be equal to Q over epsilon naught. By this relationship here, we said that it should be equal to a constant times Q, the Q enclosed. So by comparing these two, it seems like we can get agreement if that constant of proportionality is 1 over epsilon naught, which then gives us the first of the 4 big equations of the course, which is Gauss's law, that if I evaluate the flux over a closed surface, that flux is equal to 1 over epsilon naught times the Q enclosed. Again, motivated by the idea that positive charges form sources, negative charges form sinks. So when I form a closed surface, if more field lines go out than come in, that means there's some sort of source inside that is creating those field lines, a positive charge. In this case, if more field lines go in than come out, then that means they are going down some sort of sink, which for charges or for electric fields are negative charges. If there's a surface where everything that goes in comes out, then there's at least no net sources in sinks. There could be maybe one of both, right? And maybe it evens out, but it could also be that there's nothing inside in terms of charge. There's still an electric field, but the flux evaluates to 0. This is saying something very powerful because I can look over some volume, essentially. I'm looking over the surface of a volume, which could be really far away from the enclosed charge. It could have nothing to do with the charges, right? In this Coulomb's law example, right, I drew a sphere. Could have drawn a box around it. And I asked, okay, for the electric field lines, some of them are gonna go through different sides of the box. What is the flux through the surface of the box? And I would say it is, without having to do a single integral, it is Q over epsilon naught. Because Gauss's law says the flux over any closed surface is going to be equal to whatever the charge is, the net charge is inside that surface, over epsilon naught, or 1 multiplied by 1 over epsilon naught. Again, the power of this is in its generality, in that I could draw a sphere around the charge and say the flux through the sphere is Q over E. I could draw a square, or a cube rather, around this charge and ask, what is the flux through the cube? Q over E. I could draw, kind of out of room, we're going to erase Coulomb's law, sorry, to Coulomb, if he's listening. I could have a positive charge, and I could draw some, fish-like thing, going on. And it's some surface that, some sort of fish. And I could ask, what is the flux kind of through, this surface here, which might have some field lines that kind of go out and then go back in and then go out again. And I would say the net flux through that surface is Q over E. Because in all these cases, every single case, the surface encloses a single Q. And by Gauss's law, it says that the flux through all of these things must be equal to Q over E. It's one of these things that it might not be as impactful right now, but with a little bit of thought and realization, you realize this is pretty remarkable that we were able to say something like this. Because again, I could draw this surface light years away from the charge, but as long as the surface encloses that charge within it, I could tell you exactly what the flux is through that surface, the total net flux through that surface. And there could be other charges nearby. For example, I could put a negative charge over here. I'll put two negative charges over there. That's going to create, a different electric field, for what's going on. But then I could ask, what is the net flux through this fish surface? Still Q over E, because that is the charge that's inside. It's only what's inside, right? Because again, it's essentially measuring by counting field lines, in a sense, is then able to count whether there are sources or sinks. So the sources or sinks are the charges that are inside. So I could ask this problem up here. I have kind of a plus, and a minus. And then I've drawn three surfaces. This is in 2D, but you can imagine doing this in 3D. And I said, rank the flux for each surface here. Which one has more flux than the other? And if I look at the red has no charge inside of it. So the flux, which is equal to the charge inside of it, is 0. The blue does have charge inside of it, but the net charge inside of it is 0. So then the flux is 0. Same for this one. So in this case, all the fluxes are the same. And particularly, they're all 0. Because it's, again, only what the charge... And now, of course, the flux, the field lines are going to look very different going through each surface. Right? This one has kind of a dipole thing. I shouldn't use red. I'll use green. This one has kind of a dipole thing going on. But then these two pluses are going to kind of repel one another. This is probably going to do some sort of dipole thing. So kind of, if I look just at the field lines that are going in and out of each of these surfaces, they look quite different. Kind of what's going in and out of this versus in and out of this versus in and out of this. Doesn't matter. They all have the same flux, the same net flux overall, because again, the sources and sinks essentially determine the net flux through the surface. Astonishing, really. This turns out to also be more profound than Coulomb's law. It's easy to show that it's equivalent to Coulomb's law, which means essentially we proved it that if Coulomb's law, we proved Gauss's law. Equivalent means that we can now assume Gauss's law and prove Coulomb's law. So they're kind of interchangeable in a sense. There's an equivalence relationship for the math majors. But it turns out that Gauss's law is also true if the charges are moving as well. So this is actually saying something that's a little bit more than Coulomb's law, where Coulomb's law really only valid. Notice that we never had the charges moving. Coulomb's law really is only valid if they are stationary or very, very damn close to being stationary. Yeah, we could do it real quick. So essentially I want to do 3 examples of how the power of using Gauss's law, and then I want to talk about conceptual results that you can get by thinking about Gauss's law. These first 3 examples are more or less to show that we could have saved ourselves a lot of headache if we started with Gauss's law. But I don't think we would have believed me if I wrote this down on day 1. So let's take a point charge. Let's suppose I don't know anything except Gauss's law, and I want to determine what the electric field is for a point charge. Right, I'm not taking I don't know Coulomb's law, I don't know anything about E fields except that they exist, and I want to figure out what is the E field around this positive charge. Well, first, by symmetry, I could argue that I know by symmetry that the electric field has to be radial. Essentially, that is the only real option I have in this case that is going to allow me to also obey Gauss's law. And that is because, again, we can make the symmetry argument of, suppose you did not think it was going to be radial. Suppose you thought the electric field would be kind of pointing, this way, perhaps. And that was the entire electric field. Well, we can do the same thing we've done in class and in other videos, where I could say, okay, then I ask you to close your eyes. And when you open them again, you see the exact same setup. And then I say, draw the electric field. And you would say, well, it's the same exact setup, so it's going to be exactly the same as what I said before. And then I say, well, turns out I rotated the entire thing 180 degrees. So then shouldn't the answer be this? And you'd be like, drat, contradiction. The only way we can essentially invoke symmetry and not get a contradiction is if it's radial. Again, so I've now essentially proven or argued that it should be radial, but I don't know what its magnitude is. Well, the first thing I would do is I would pick what's called a Gaussian surface. So essentially I need a closed surface. Right, if I want to use Gauss's law, right, the idea is I need a closed surface. But as I tried to motivate in the previous questions, or the previous parts rather, I can choose any surface I want. It just has to be closed. But I'm going, so maybe I'll use a cube, or maybe I'll use that fish thing. Now, of course, I could use a surface that is going to make my life simple. And if the electric field is radial, and I know I'm going to have to dot the electric field with the area vectors, why not use a Gaussian surface that's also kind of spherically symmetric, i.e. a sphere that has some radius, little r. Something I also didn't mention before is, by saying that the electric field is kind of radial like it is, or it points radially away from the positive charge, also means that the only kind of variable it can depend on is r. It can't depend on just x or y or z, because then if I rotated it, things would look different. The only variable that could appear in the equation has to be r. So the sphere, and we've done this problem already, then essentially means that E is parallel to dA, because all the little dA elements, I should use a different color, all the little dA elements that point away from the surface and are perpendicular are also pointing away from the center of the sphere. And so in this case, the net flux through this surface is then going to be the integral of the magnitude of E times dA times the cosine of the angle between them, but we just argued that the angle is 0, and that the magnitude of E is the same everywhere on the sphere, because everywhere on the sphere is the same distance away from the center. So then this just becomes E times the full integral of the sphere. So I know then that E is 4 pi times 4 pi r squared. Then by Gauss's law, right, so then this must be equal, if Gauss's law is to be believed, this must be equal to then Q over epsilon naught, which then of course shows that E is Q over 4 pi epsilon naught r squared. And we argued that it points radially away. Given that it's a positive charge, right, this also shows that for positive charges, the electric field must point away. You know, if they pointed radially inward, we would have gotten a net negative flux, which would not have agreed with Gauss's law since there's a positive charge. So this also incorporates that the electric field goes away from positives and towards negatives. So again, kind of a key here is that the surface can be anything you want. So of course, pick something that is wise, that makes your life easy. And essentially that means that you either draw a sphere or a cylinder, or what's, I think, something that's called the Gaussian pillbox. So let's try the wire. How could I evaluate the electric field of an infinitely long wire? Well, again, by symmetry, we know that E must point kind of away from the wire. And away in that it makes a 90-degree angle with the wire itself. Right? These are all 90-degree angles. Again, if that was not the case, like if one of these actually pointed this way, then I could, again, make you close your eyes. I may or may not rotate the thing. And if I did rotate it, then this one might rotate to be over here. But you wouldn't know any different because it would look exactly the same. So again, the only way I can match that, is if I have things pointing what I'll call radially away, even though it's not really radially from a point, but kind of radially from the line. So then, what sort of shape helps me in this case? Well, I'm going to draw a cylinder that's kind of centered on the wire. All right, so its center also, the wire essentially goes through the center of the cylinder. And this is going to have some radius, little r, and some length, call it capital L. But again, remember, we know that the electric field, by symmetry, must point away. So in evaluating the net flux through this surface, essentially there are three sides to the surface. There's, let's use colors. There's the top. There's kind of the shaft of the cylinder. And then there's the bottom. So in this case, the total flux is just going to then be the flux through the top, the flux through, we'll call it the side, and the flux through the bottom. But then notice that this shape makes two of these super easy. Well, actually it makes all of them pretty easy. It makes two of them really easy. Let's look at the top. Here's the surface, which has some area vector that points perpendicular to it. I'll just write it as A. I'm not sure what's happening right now. And then I have the electric field lines that are pointing radially away. And notice that they are perpendicular to A. None of them actually go through the top and the bottom. Because in that case, they're essentially, if they're at 90-degree angles from one another, again, think of the water. The water stream will not go through the sensor into the bucket. So in this case, the electric field over the top, since they make a 90-degree angle with one another, the area and the electric field, right, the cosine of 90 degrees is 0, so this flux is 0. No field lines go through. Similarly, for the bottom, it's also 0, because no field lines go through the bottom either. So it seems like then the flux, the total flux, is just the same as evaluating the flux through the side. Now for the side, I can redraw. The area elements, the little dAs, again are all nice and parallel to the electric field, because they also are pointing kind of away from the center of the cylinder. So we once again got this situation where this is going to equal the electric field, and just the integral of dA over the side. Because the electric field then, again, by symmetry, must have the same magnitude everywhere on the side. This then is just E. Now the area of the side, so you can think of it, it's 2 pi r multiplied by the length. Essentially, take 2 pi r, which is the circle, and then I have L of them, right, to create the entire side. And by Gauss's law, that must be equal to the charge enclosed divided by epsilon naught. But the charge enclosed, I have some snippet of wire that's inside the cylinder. I have this entire wire here that has a charge density lambda naught. But then essentially you can imagine just cutting off a piece of it that has length L. And I could ask you, I've asked you several lectures ago, what is the total charge on this finite length of wire? It has length L and a charge density of lambda naught. Well, in that case, then it's just lambda naught times L, all over epsilon naught. And then notice that the L's cancel. And at the end of the day, we get that the electric field looks like lambda naught, then I have 2 pi epsilon naught times r. And it points, this is what I was calling r perp, r perpendicular. And if you look back on your notes, you'll notice that is exactly what we derived after doing some integrals, through a slightly more involved way. Essentially, we got it pretty easy just by looking at the flux going through this tube. So again, this should feel almost like magic until you do this a couple times, work through these problems, and the ones we'll do in class, and you really start to see kind of what this is doing. Because again, the line of charge is essentially a line of sources where the electric field can emerge from. And we're essentially just accounting for all the sources that are kind of within a particular cylindrical volume. One more, and then we go to the concepts, which I think are more interesting. The infinite sheet. We essentially needed 2 lectures to get to the infinite sheet, because we had to do the loop, and then from the loop we went to the disk, and then from the disk we went to the sheet. We didn't even do the disk, really. I skipped over that derivation. And we ultimately got that the electric field was a constant and it was equal to sigma naught divided by 2 epsilon naught, and pointed away from the sheet. Well, again, we could try to do a Gauss's law version. By symmetry, I know that the electric field, again, must point away from the sheet. Again, if it didn't point away, imagine me rotating it. Same sort of argument. So I know the electric field must point kind of away from the sheet. So since it points directly away from the sheet, I should pick a surface that will ideally have the electric field be parallel to some parts of the surface and then maybe perpendicular to other parts. So kind of the cylinder again comes to our aid. But the cylinder is going to kind of pierce down through the sheet. So part of the cylinder is going to be underneath the sheet, and it's going to come up and go above the sheet as well. That's a closed surface. You can imagine that there's a volume that I've kind of enclosed, and there's some charge that's enclosed as well. Essentially that little, let me zoom in. Whoop. Even now my highlighter is too big, but I think you get what I mean. Like that part right there. How much can I zoom in? I guess I can change the size of this. Yeah, that part right there essentially is kind of a circular little chunk of charge. It's the part of the sheet that is kind of clipped off. If you imagine this being like a cookie cutter, and you slammed the cookie cutter down into the sheet, right? You would cut off, that purple, circle of dough. But we're going to consider the cylinder that kind of has a part above it and below. So let me redraw it here. All right, so again, here's the kind of piece of charge, the charged dough for you, given the kind of analogy I just came up with. Actually, it's a pretty good one. So the electric field, we argued already that must point straight away from the charge. And again, notice how this helps us. Because the electric field seems to be pointing parallel to this surface right here, my little dA. It's pointing, or I could just use A because it's a flat surface. The electric field is pointing parallel to that one, so it's pointing parallel to this one, right? There's a dA there. But then for the sides, right, the kind of part that goes around here, the electric field does not go through that side, go through the sides of the cylinder. Because dA would point this way, or this way, or this way. And the electric field only is vertical, so there's no flux through the side. So then the total flux, which is going to be the flux through the top again, flux through the bottom again, and flux through the sides. In this case, it's the side that's 0. And it's the top and the bottom that are the ones that have flux. And by symmetry, again, it looks like it's just going to be 2 times the flux through the top, say. So it's going to be 2 times the integral of the electric field, at the top, dotted with dA. Which in this case is just going to be 2 because they're parallel to one another. Technically, it's the magnitude of E. And A is going to be the area of that circle is going to be 2, or the area is going to be pi r squared times E. And by Gauss's law, that should be equal to the charge enclosed over epsilon naught, which for a 2D charge density, it's going to be sigma times pi r squared. This is going to be the total charge divided by epsilon naught. And then notice what happens. You got the pi r squareds canceling out. And at the end of the day, you got that the electric field is going to be sigma naught over 2 epsilon naught. And you can make this a vector again, because we argued that it should point away from the sheet. So I'll use rperp to again be away from the sheet if it's a positive charge density. Negative charge density points toward the sheet. So that did not take us 2 lectures to get. And it really just amounted to us being clever about which surface we drew. Because again, could have used a box that went through, and maybe that would have worked too, by the symmetry of the situation. You could try that, right? Do a rectangular box that kind of, that's a cookie cutter sheet that goes through the infinite sheet. There's a part of it that gets clipped off that has some charge. It's going to be some rectangular piece. You could figure out the total charge as a function of the dimensions of the cube or rectangle, and you should get the same exact answer. Actually, now that I've thought of that, that's going to be on our sheets for class. You could have used something else. You could have used something like a hemisphere or something. The integral would have been much, much harder because you would have had to do the integral of all this vertical electric fields through this curved top. So by us choosing this, we made our lives easier and utilized both the symmetry and geometry. You can look at the book for other derivations of this. And an upper level EM course would spend its days just evaluating ridiculous Gauss law integrals, which you'd be able to very simply with this result. I would rather focus on the conceptual understanding of what this tells us. Again, we should be able to state kind of what it means, right? That it connects the flux through a surface to the charge enclosed. Now let's actually use it to understand stuff about conductors. So let's start with, you have a solid piece of metal. There's my 3D drawing of a chunk of metal. And you give it some excess charge. What can we learn? So we could ask ourselves, like, what is E inside the conductor? Where is the excess charge? What is E just outside the surface? I'm going to use the 2D example, just because it's easier to draw. The caption can go with it. All right, so I've given it some net charge Q. What can I learn? This first one we don't actually need. We could have done weeks ago, actually. What is E field inside the conductor? So if I dump some charge onto the conductor, right, eventually it will settle into some equilibrium configuration. Where the charges are stationary. If that were not the case, that would be perpetual current, right? You'd have charges moving around indefinitely. That does not happen. There's not a semiconductor. So eventually the charges will settle into equilibrium, which means the charges, wherever they are not moving. So what does that mean about the electric field inside the conductor? So the charges move. Well, a charge is going to move if there's a net force on it. If it's stationary, it will stop being stationary if there's a net force, because that will cause it to accelerate, which will cause its velocity to change from being non-zero. So if you have, maybe I'll use plus E, right? If that's stationary, right, there needs to be some sort of net force to get it to move. But if it's stationary, Right? If it's stationary, then that means F net is 0 on all excess charge. Again, if that were not the case, there'd be a net force and the charge would start to move. But then, what forces are actually causing the charges to move? It would be the electric field from the other charges. If I had some plus here, or some pluses over here, presumably it's those pluses and minuses that are going to make this thing move. So the forces arise from the electric field of the other charges. So if F net is 0 on the charge, but then I know that the forces, F net, which is the sum of forces, individual forces, right? I could write kind of the individual forces kind of on Q from kind of other Qs or other charges, which gets a little messy. So we'll just look at, for one of these excess charges, the net force on that charge will cause it to move. And that's the result of kind of the inner charge interactions, which we know is just going to be that Q sub I times the electric field from the other charges. And so that's just going to be Q multiplied by the sum of the E fields from the other charges. Or that's just going to be Q sub I times E net. Right? The net electric field from all the other charges on the conductor. But we just said that that's 0. So that implies then that E is 0 inside a conductor. Again, the argument being, if the charges are stationary, then there cannot be a net force. But those forces, the only forces that really could operate are essentially the other charges creating an electric field that then that charge responds to, which amounts to that the net force on the charge is Q times the net electric field at wherever that charge is. But if that is 0, then that means E net is 0. So anywhere inside the conductor, E is 0. Inside the conductor. Now there's still all those extra charges. We haven't said where they are. I believe in class you gave an argument of thinking probably on the surface, because that allows them to get as far away from each other as possible. Turns out that's correct. Let's actually prove it. And we can do this by our good old Gaussian surfaces. But here I'm just going to draw some arbitrary surface. Okay, so it's some arbitrary surface inside the conductor. All right, so it's entirely enclosed inside the conductor. But what it looks like and where it is, I'm not telling you. I'm just telling you that's inside the conductor. Well, by Gauss's law, we know that the flux through that surface better equal the enclosed charge over epsilon naught. But I just said E is 0 everywhere. Inside. So then this integral is just the integral over 0. Which is itself just 0. So there is no net flux through this surface. That's equal to Q enclosed over epsilon naught. So that means that Q enclosed must be 0. That means that excess charge cannot be inside that shape, that red shape I just drew. Also means it cannot be inside this blue shape I just drew. Also cannot be inside this green shape I just drew. Essentially, I could imagine drawing a surface that's essentially just a sliver kind of inside the surface of the conductor. And it's entirely inside. Right, so E is still 0 everywhere along that surface. So then the total charge, this excess charge, cannot be inside the purple surface either. So essentially all of this collects to say that Q must reside on the surface. That's essentially the only place left. Because if it resided anywhere inside, Gauss's law would be disobeyed. Because we could then draw some surface around it. But since the electric field is 0, that flux is going to be 0, which then contradicts what we claimed, unless the charge is entirely inside. So this shows that the Q must reside entirely on the surface of the conductor. Let's see. Yep, I need a new page. I took up too much room. Let me copy this. So we have, in this case, the electric field is 0 inside, and the charge, which let me just take it to be positive, is going to reside entirely on the surface. So then the last question was the electric field just outside the surface? Now I could do a Gaussian surface that kind of hugs the entire thing. Turns out to not be that useful, because then the flux through that surface then is just going to be Q over epsilon naught, the enclosed charge. Doesn't really tell me anything about kind of the direction of the field, right? Because I could imagine a bunch of different ways I can draw field lines such that the net flux is Q over epsilon naught. So what's going to be helpful, let's see. Is that I'm going to draw, essentially I'm going to zoom in. And I'm going to draw actually a little pillbox again, kind of right along a little part of the surface. So let's suppose we zoom in here, right? So here's the surface. Right, there's some positive charge hanging out on the surface, and it's spread out. Right, the charge is spread out over the surface. So, with kind of Q spread over the surface, right? Then every point on the surface has some local charge density. Has a local, meaning it's not uniform everywhere on the surface, but some local charge density. I will call that sigma local. right? And it's different at different places. Turns out that if you have kind of kinks or points, the charge density is usually higher than if it's kind of in smooth areas. That's essentially why lightning rods are lightning rods. That the electric field, well, the charge density on the tip of the lightning rod builds up compared to if I just like held a giant ball or something. We might work through that derivation in class. But here's kind of a zoom in, back to the problem. Here's kind of a zoom in where we have the conductor, and then there's the surface where charges are hanging out. I'm going to draw essentially, in my pillbox is going to be essentially so slightly above the surface, ever so slightly above the surface, and then it's going to kind of puncture into the conductor. So this is just kind of just barely above surface. Essentially, we're saying that it's on the surface, but it includes the surface. It's not just below the surface, it's just above the surface. Now again, the charges are stationary, which means they're stationary charges, which means that E net is 0 kind of along the surface, right? Because just above the surface, right, you're going from conductor to air, or conductor to some other material. So the charges are not going to, the charges on a conductor, right, can very easily move around on the conductor. But we could even say that, suppose that this is in a vacuum, right? So the charges aren't going to be able to just leap off the surface. So the charges, if they are going to move, can only move kind of along the surface or into the conductor. Well, we've already said they aren't in the conductor because the electric field inside the conductor is 0. So the charges, if they're going to move, are probably going to move somewhere along the surface. But they would only move if there's a net electric field, along the surface, right? Essentially parallel to the surface. That would mean that the charges move. But we just said that they aren't moving. We just said that the entire thing's in equilibrium. So then this argues implies that E, on the surface, must point perpendicular to the surface. If it did not, then that means there would be a parallel component, a component of the E field parallel to the surface of the conductor, and the charges would start to move. That would be a contradiction. We said they're not moving, which means any electric field on the surface must be pointing perpendicular to the surface. So the electric field must, at every point along the surface, make a 90-degree angle with it. Okay, that's good. That's one thing. That's another thing we've learned. Now we can use Gauss's law again, but use it for this whole thing. Now, if I just said that the electric field points away from the surface, again, that means the sides aren't going to contribute any flux because the electric field does not go through them. And in here, we said E is 0 inside the conductor. So there's no flux through the bottom of the cylinder. There's only electric flux going through the top of the cylinder. In this case, the electric field, or the total flux, is just the flux through the top of the cylinder, which in this case is going to be kind of sigma, we'll call it E perpendicular times A, a little kind of we'll just say the area of kind of the cylinder top. And by Gauss's law, that must be Q enclosed over epsilon naught. The Q enclosed is going to be the local charge density times, I guess, A, divided by epsilon naught. Again, these are arguments now we've done multiple times, which is why I'm going fast. Total charge and is charge density times an area for 2D, etc. So then this implies that the electric field perpendicular to the surface has a magnitude equal to kind of the local charge density divided by epsilon naught, which looks a lot like the infinite sheet. But remember, for the infinite sheet, it was the same charge density everywhere. Here it's the local charge density, right? So that across the surface of a conductor, this charge density will be different. And like I was saying, essentially was giving away the answer, right? So lightning rod, essentially when you have sharp points, turns out that the kind of local charge density here becomes high compared to, elsewhere. Okay, here local is low. And as a result, there's kind of a very strong electric field that forms at points, which then which then increases the chance that that's going to be where the electric field gets strong enough to actually, create lightning or have lightning strike. That's also why they say, like, if you're in a lightning storm, don't hang out, in an open field, because essentially that makes you the point. And as a result, the electric field builds up and is stronger on you compared to your surroundings, which then is possibly where lightning strikes. Yeah, like they say, there was some viral video a couple years ago where it was some woman, it was like a Snapchat she did, where she was like in this area where clearly a thunderstorm was like moving in, and she was taking this video of herself because she was like captivated by the fact that all her long hair was suddenly getting staticky and started to like float out of nowhere. And then everyone that was watching the video essentially was like, run for your effing life. Because essentially the electric field was building up around her, and she was becoming a lightning rod. So don't do that. Or when they say avoid being near a tree. The tree essentially then is the lightning rod, if there's nothing else nearby. So that essentially comes out from these sorts of arguments. All right, so we learned a lot about conductors, right? The E field is 0 inside. The charge is all on the surface. The electric field at the surface is perpendicular to the surface and depends on the local charge density, which it's a couple more steps. That's easier to show once we learn potential, which is the next topic, right? Which then you can use that to show that like lightning rod, like at points, the charge density is higher than on like the base, for example. Okay. What about if I have something like I have a charged conductor, but there's a hole in the middle? So here's a 2D example, right, where you have some charge, you have some conductor, and I'm going to plop some Q on it, but then there's a hole in the middle. So is Q still located on, because we said that Q goes to the surface, but now technically there's two surfaces. Is Q on the outer surface, or is it kind of shared between the outer and the inner surface? And what's E inside the cavity? Well, we can make kind of the same sort of argument, right? So then Q kind of goes to equilibrium. And you can repeat the argument to show that E must be 0 inside the conductor. So see if you could retrace that argument to show that. So everywhere inside the conductor, the electric field is 0. If I then draw a Gaussian surface that's, say, dotted. If I draw a surface that's kind of entirely inside the cavity, then the flux, in this case, is 0 because Q enclosed is 0. Right? The charge is on the conductor, so the charge is not inside the cavity, but somewhere on the conductor. So the electric field inside the cavity is 0. That might be helpful. What if I were to draw another surface that's just hugging inside the conductor? So it's kind of the blue you could think of, the blue I really could have drawn anywhere inside the cavity. But imagine I drew the blue kind of just on the inner edge of the cavity. There the flux is 0 because there's no charge inside the blue kind of dotted line I drew. Now for the red one, I drew it all entirely just inside the surface. Well, then I say the flux is still 0, but this is because we just said that E is 0 inside the cavity. And that dotted red line is entirely inside the cavity, so everywhere along it, I'd be evaluating E dot dA, but that E is 0. So, it seems if I'm just on the inside of the cavity, there's no, so then by Gauss's law that says that the enclosed charge is 0. So just inside the cavity, there's no net charge. Just on the other side of the cavity, inside the conductor, there's no net charge. Seems that it's implying that Q is not on the inner surface. And you can also show, we have essentially argued, that you could kind of fill in the steps, right? This also then shows that E is also 0 inside the cavity. And Q, again, is on the outer surface. And again, you could do a Gauss's law sort of argument again, right? Draw your surface just on the inside and then maybe do another one just on the outside, for example, or like what we did before with the pillbox. And you can reach the same, essentially the Q is entirely on the outside, the cavity on the inside is 0, or has no electric field, so the electric field inside the conductor is 0, but then the electric field inside this hole is also 0. And that essentially is the basis of a Faraday cage, where in this case, the charge in the conductor kind of redistributed itself so that the electric field everywhere inside vanished. You could also have, a conductor with inside some ambient electric field, in which case, if electric fields, point 2 negatives from positives, then negative charges are probably going to collect on this side, which are going to leave positive charges left on this side. Even if the conductor is neutral, right, charges might kind of separate. So it's still overly neutral, but just kind of redistributes itself. In this case, again, the charge finds equilibrium, but then all the results follow. E is 0 inside cavity, inside the conductor. And really it's this E inside the cavity that I care about right now. Essentially, the conductor will make sure that the electric field inside the cavity is 0. So that if there was anything precious inside that cavity, say you, you would at least be assured that the conductor is making it so that there's no electric field inside there. You have valued Faraday cages all your life, perhaps without even knowing it. Your computer case is essentially a Faraday cage. If there is any excess charge that gets dumped onto the exterior of your laptop or your desktop, they will rearrange themselves on the conductor, just like this, so that there's no electric field inside, which, for all the electronics that are inside, is a good deal. Your laptop case, your desktop case. That's why they also say, like, if you're, like, I used to always like, taking my desktop, apart, right? Because I would buy like more RAM and whatnot. I want to install it myself as a kid. But they would always recommend that you kind of touch the case of the computer before you start touching all the electronics. Essentially, you're trying to ground. In that case, you're trying to ground yourself. You're trying to dump the charge onto something else. But then also that charge itself, if the case is kind of still over the computer, will keep the electric field kind of in check, which that might also include you. Microwaves. Have you ever wondered why it's safe for you to just kind of hang out right next to a microwave and salivate, as your meal cooks, and that radiation is not, like causing bad things to happen? Well, it's because the microwave itself is a Faraday cage. That's why usually if you look at the kind of viewing screen, like it's usually not just completely clear, but if you look close enough, like it's usually, you can see like some metal mesh that kind of, with holes in it so you can see through it. But essentially, the case of the microwave acts as a Faraday cage. So all that radiation, which turns out is just a bunch of electric fields, essentially can't get out. In that case, kind of an inverse Faraday cage. Same sort of process. Metal wallets. My wallet. Let's see. Do I have it nearby? Sorry to wake you, cat. Let's see here. The webcam doesn't even want to turn on. Oh, that was a bust. I guess I could show you in class. Essentially, the wallet itself is essentially a little metal box, right? And it was advertised as being right, like people can't scan your credit cards, if it's in this box. Essentially, modern credit cards that have the little chips in it. Essentially, and we'll learn about this when we talk about magnetic induction. Essentially, devices make the chips essentially create electric and magnetic fields that can get transmitted into signals. The Faraday cage means that them trying to go in and read the signal that might come out. Essentially, this if they're trying to get the signal to come out, the wallet will prevent it from doing so. Prisons are usually constructed to be this way too, right? So that any kind of contraband cell phones that are smuggled in, essentially they get terrible cell service. This is also why usually your cell service goes to crap when you're inside an elevator. Also, the same reason why, going back to our previous example, why if there's a lightning storm, the safest thing you can do is get in your car, because your car will act as a Faraday cage. It's not because of the rubber tires. Big misconception, right? They think that the rubber tires prevent the car from being grounded, so then current won't flow through. That's not really what's going on here. Essentially, lightning. If you're in the car and lightning strikes the car, right? Just don't be touching the outside. Don't be touching the frame, and essentially the frame of the car will act as a Faraday cage, and you'll be perfectly safe inside. Though I'm sure that would be ungodly terrifying. But again, essentially the charge on the surface will redistribute itself rather quickly, actually, such that the electric field inside will become 0, and you'll be fine. Your car, I don't know. So, good idea to understand kind of the idea of this Faraday cage, right? The fact that the E fields can go to 0 inside. Then I'll leave you with kind of one to think about, just kind of the last kind of possible case of conductor, cavity, but then what if there's a charge inside the cavity? You might try it on your own, of just kind of, drawing kind of Gaussian surfaces kind of around in the cavity, and then just inside the cavity, and then along the edge, inside the conductor, and then outside the conductor, and thinking about which are going to have 0 net flux, 0 charge enclosed, right? And take the conductor to be neutral. So there's no net charge in the conductor, but then there's this charge inside the cavity. Which of these kind of results follow through, whatnot. So there's a lot here. And again, I think it takes probably more than one class to fully appreciate Gauss's law, but I won't really we've done kind of evaluations of flux and whatnot, and you might be able to do, I might ask you to do kind of simple evaluations of connecting flux to charge enclosed, but nothing super calculus-y. But conceptually, notice that these were all kind of conceptual ideas of just kind of working through those and seeing what was the arguments that we made here, and that your book kind of walks through as well. Those would be good, I feel, to understand. All right, very good.